All right, thanks, Paul.
Okay. All right. Well, I have to be on my best behavior, I guess, because we are recording it now. But welcome to this discussion, this primer on celestial navigation. It is Pi Day, so I have to make a big point of that. I have my red Pi socks on. I feel in the moment. Okay. So what are we going to do? Well, my goal here is to follow this outline, and I am not going to delve into the very details of the math, and I'll explain why. But we are going to hopefully understand what it is that celestial navigation is, and why do we even want to do it in the first place? Well, a little bit of it's the mystery and magic of things like ham radio. It's always fascinated people for a long time. There's a link here in the presentation that you can also click on and find out a little bit more about mystery and magic in ham radio by one of our club members, W1MBF. I'm not going to play it because of time constraints. The other thing I want to talk about are what are the tools that are used to do celestial navigation. What are there are alternatives, and I want to talk about that. It's very important that you try to understand what a ground point is. The ground point of a heavenly body is a key element to what we're trying to do and what we want to compute. I'm going to talk about times, various kinds of time, although because there are more than one, and a thing called assumed position, which is sometimes referred to or often referred to as DR or dead reckoning position. I'm going to talk about how to find the ground point. We're going to talk about what it is, but then we're going to talk about how we actually find the ground point of a celestial body. And from that information, we come to the conclusion, where am I? And how we would find our exact position on the Earth's surface or someplace else. Last reason for doing it is just fun. And I hope that's not above your head in the colloquial sense. The stars are above your head. This is the point. And if you have questions, enter them in the chat so we can move this along. But oops, sorry. And I'll try to answer them in the last 10 minutes. I am moving. Whoops. Okay. So what it is? Well, it's really a technique for finding your location using the objects in the sky, and that's why it's called celestial. And we do hope that part of it is over your head. You will produce from these computations a latitude and longitude estimate. It will not be as accurate as your GPS unless you're really, really good at it. Chances are it won't be. It's really an estimate to correct a position that you think you're at, and we'll talk about that. Another thing about celestial navigation is it's been used for millennia. I mean, the Polynesians used it. Lots of people use it in all different types of ways. So it's a historically significant technique that I think bears some understanding. It's a useful thing to know in general. One of the other things is that it is resilient to failures in electronic navigation. We're all exposed now to GPS and high quality positioning and so forth. If that system is taken out for some reason, and it's very easy to take out, in my opinion, we would still be able to rely on celestial navigation, even if we didn't have a computer. All we needed were tables. But if we had at least a Casio calculator or something, or a calculator, we'd be able to do it. And another thing about celestial navigation, it's not just about where you are on the Earth. It's about where you are in general. And so there are a lot of space aspects of celestial navigation. And we've got some links at the end on the sextant used in the Apollo mission, the International Space Station, and some deep space techniques for doing celestial navigation in deep space. Even if you don't want to know where you are, celestial navigation is also handy for finding where the stars and planets are and the moon. So if you're doing moon bounce, you might want to use the same techniques to figure out where stars are, which is part of the process. You find stars and planets, then you find out where you are relative to them. So it's handy for finding those things, even if you're not trying to find for your location. And if nothing else, I think it's a lot of fun. Okay, so what kind of tools do we use in celestial navigation? Well, the important thing is we want to measure angles. And the classic thing for measuring angles at sea is the nautical sextant. But actually, all we're really doing is measuring angles. So we could use anything that measures angles, including a protractor or a very expensive piece of survey equipment. The important part of finding angles is to find a level surface or where, and you can do that a number of ways. You can use bubbles like on regular levels. You can use the horizon, which is very far away and is a way to position the sextant. Or you could use a pendulum and just find out where level is from a pendulum. And some of those tools go way back to the Babylonians and so forth. So the important thing is you're trying to find where level is. And in a nautical sextant, we're going to talk about the horizon is that technique. Another very important part of this is to find out what time it is. Without time, most of this would be useless except for possibly latitude. If you really want to know where you are, you're going to need a good clock. Lots of ways today of getting a good clock. Many years ago, there wasn't one. We could talk about that ad nauseum as well. That's another whole subject. But we need to find, for instance, the local time at our assumed position. We need a watch, but the watch has to be calibrated against something else. We really want to know very accurately what time we took that angle at. We're talking a second is a long time. We normally write down what we did to a second, but if we're 2 seconds off, we're going to be far away from where we think, where we calculate. There are lots of tools for doing time measurement. As you know, you have watches. There are things on ships that are called chronometers, and they're very accurate timepieces. You can also get time from your radio. WWV broadcasts on over here, 2.5, 5, 10, 15, and 20 megahertz. You can also get time very accurately from the National Institute of Standards time link on the web, which is what most of your computers are actually synchronized to. If you really want to know, I'm not sure this figure is even accurate anymore. It's at least 1 second in 300 million years, but we could probably do a little better than that today. But if you want to get that accurate, you can. We do not need to get that. We need that accuracy, but we don't need to measure it to do celestial. You could use your cell phone, perfectly good. It's synchronized to the same atomic clock that all of this is synchronized to. Or you could have a fancy GPS clock synchronizer, which would synchronize to the GPS system, which also doesn't only give you position, it gives you accurate time. And the other tool you need to, the other tool you need is computation. You have to compute where these ground points are. And you can do that with a number of things. You can do it with tables, you can do it with calculators, you can do it with computers, obviously. Excel and so forth are great tools for that. In the past, people ran around with huge tables and no calculators, except they would add and subtract. Now, with a multiplying calculator, it's much more practical to just do it without a big book. But if you have the book and your calculator runs out of batteries, you can do it. So it's very resilient to know where the tables are and maybe have a copy of them if you felt you needed that. I have put a link in here, which you can't see because it's covering my screen, but anyway, there's a link in here on how to get a copy of the Nautical Almanac online. Everything that I'm talking about tonight is online. You don't need a book. You can certainly buy plenty of them, but I'm hoping that you have enough links to do everything with online information. One other interesting thing, if you get, I got my April QST today, and on page 66, the WWV people are transmitting a special signal for science, citizen science, and you can participate by listening to WWV in a way different than just getting time. So if you got QSD magazine, take a look at the bottom of page 66. Interesting. Okay. Well, the real tool here that everybody likes to talk about is the nautical sextant. It looks like this, or it might look like this. This is an inexpensive one. The one shown there, this is the $57 one. There's plenty of them that you can spend a lot of money, more than $1,000, more than $500, depending on accuracy and how shiny it is. But anyway, what is it for? Well, it's there to measure angles again, usually to the minute of arc. We'll talk about what a minute is, but you're measuring that angle from the horizon, which is the surface on the water here, which is a really handy thing when you're in the ocean. And it's not so handy if you're sitting in the middle of Aquidneck Island where you can't see the water. So this horizon thing is very important for being at sea, but it's useless on land. What you really want to do is get a point of leveling so that you know where you are with respect to some reference, which in general is level. When you look in the sextant over here, what you'll see is a split image, and you'll see that what you're looking at directly in front of you, which is nothing more than what's in back here. And then you'll see the object. If you move this lever in the right position, you'll move this object into position near this line. So the whole thing is to move this arm until this body that you're looking at, whether it be the sun or a star, lines up with the horizon. Now you see in this picture, it's lined up at the middle. That's not the place to do it. The place to do it is actually on the bottom edge. We'll talk about that in a minute. All right, so you're measuring an angle. The sun is up in the sky here, and we're measuring this angle, and we call that angle altitude. Not the height above the ground, but the angle is altitude, and we give it a name H. So in the math, you'll use the symbol H with some suffix to mean which H you mean. The first sextant was developed by John Bird in 1757, so it's not an instrument in its current form that was used much earlier than 757, which, by the way, is around the time of Newton and about the time that we actually got a clock that worked. Prior to that point, we didn't have any good clocks, so doing all this very accurately was, I wouldn't say useless because of the thing we're going to do Saturday, but certainly the precision in navigation came after a good clock occurred and good sextants existed. Another interesting thing about the nautical sextant is that the horizon is not always visible to you. I talked about being in the middle of the island and not seeing the thing at all, but there's also cases where there's things like clouds, fog, and other things. So the technique is not available to you for sure all the time. You have to have at least some decent weather, or you have to have enough twilight or enough daylight, and that's why I use twilight, to see where the horizon is. If you in the deep of night without a moon, you're not going to see the horizon. So again, you can't do this late in the middle of the night, typically, even if you're at sea. Okay, so some factoids. What's a minute? Well, a minute is a 60th of a degree. There are 60 minutes. These are small. You probably get some idea what a degree is. It's one little mark on your protractors. Everybody's seen a protractor. A minute is 1/60th of one of those little lines. Pretty small number, but we can actually measure even smaller than that. We can divide them into seconds, a 60th of those. Measuring 1 second is very precise. It's very difficult to do. Measuring a half a second, which is, a half of the minute, 1/2 of a minute, which is 30 seconds, can be done with a decent sextant. So, but these plastic ones are only going to give us accuracy to about a minute, pretty accurately to a minute. All right, so an example of a H, that is an altitude, is the observed altitude. That's what we observe, HO. And it could be written this way: 45 degrees, 30 minutes, 6 seconds, which is 45 degrees, 30 minutes, 6 seconds. doing angle conversions is necessary in most of these calculations unless you're doing it on a spreadsheet or something. And so this is a little bit tricky, and I'm not going to spend a lot of time on it, but just to give you an example, if I want to convert 45 degrees, 30 minutes, 6 seconds, I have to take 45 degrees. If I want to do it to degrees, I have to take my 30 divided by 60. And then I've got, how many minutes have I got here? I've got 6 divided by 30 minutes. So I've got 45 degrees, 30 over 60 is a half. And I'm going to divide this by 60 again, that's the 10th. So if I add all those numbers, I'm going to have 45.501666666 degrees. This is a handy calculation to know how to do. Some people do it pretty easily, some people don't. Another interesting way to do it is just to do everything in minutes. So you can multiply your angle by 60, add 30 minutes, add this, and you can end up with 2,730.1 minutes. If you like doing everything in minutes, that's okay too. It takes a little practice to get this thing. What else would you do with a sextant? Well, maybe you want to know how your antenna is. That's an amateur radio thing. If you want to find that out, you can pick a point where your eye, the height of your eye, and then you set your sextant to 45 degrees and walk away from the antenna. And until you see that the top of the antenna is 45 degrees. And then you just measure the distance you walked, and that's how high your antenna is, but you should add your height to it because you, again, were level. Unfortunately, my, hold on a second here, sorry. In this, I can't see my own picture here because of the way the screen is, but you can see it. Basically, you've got level from where your eye is, not where the ground is. So if you take the sextant and you point to the bottom of the tree, you're going to get the wrong answer. So that's what I'm trying to tell you there, not how to measure your antenna. But it is a handy device for measuring height of anything. And it doesn't have to be done at 45 degrees, but there you go. All right, a couple of cautions. Do not look directly at the sun. I have to caution you on this because sextants have very special filters, which you see over here. And they turn in and out into this. They can be moved one or both. And always make sure you have a filter on first, then back it off if you think you can't, if it's something's too dim. But don't look directly at the sun. There are also little things over here called horizon filters, which are good for taking the reflection off the horizon, but they're not really sun filters. So don't use those for sun filters. And another little, sometimes not known fact is that if you were a navigator in the 1600s, you were always looking at a sextant or looking at the sun without a filter. And blindness was a real common occupational hazard for many early navigators. So do not do that. Okay. All right. So it's important that we separate a thing. So now we're going to get a little bit into the nitty gritty here. There are things called hour angles and there are things called hours. Well, hours are not strange. Hours are what you know, but hour angles are really like a longitude. If you don't know what a longitude is, then I'm maybe backing up a tree here, but longitude is how far you are around the earth, and you need to measure it from something. So you measure it from something like Greenwich, England. And that's, if you measure it from Greenwich, England, it's called a Greenwich hour. Whoops, sorry. It's called a Greenwich hour angle, or GHA. So it's really just how far are you in longitude from Greenwich, England, not Greenwich, Rhode Island. And there's another type called the sidereal hour angle. See this term SA all over the place. And it's measured from the GHA, or of the first point of Aries. Now, we're going to talk about what that means, but basically all the stars are measured not with respect to Greenwich, but with respect to another moving point on the earth, and we're going to talk about that. So let me just mention that now, that there are things called hour angles, which are angles. An angle could go all the way around the earth. The biggest hour angle is going to be 360 degrees. And we're around 71 degrees from London, from Greenwich, sorry. Okay, anyway, now hours are just what we think of as time, but in celestial navigation, there's more than one type of time. There's an average time, which is like, how long does it take us to go? If we move seconds and we count them, when do we get to the end of a year? But there's another time, which is a lot less obvious, called sidereal time. And I'll illustrate that in a second. But if you measure your clock, your watch or whatever, there's 24 hours in a day, and that divides the day in based on an average for the year. The real world isn't that simple. However, just a couple interesting points. If we go all the way around, that's 360 degrees. If we do that in 24 hours, we end up with 15 degrees of motion for every hour of time. Now, you typically notice that in time zones. Like New York is in the time zone that happens to match 75 degrees. It's an increment of 15. So this 15 degree number is one time zone, and it comes from doing all the way around divided by 24 hours. Okay, so that's a degree, but we also want to measure smaller angles, and 1 minute is 1/60th of a degree. Now, we've talked about that. It's just dividing into 60. So 60 minutes is 60 of those minutes adds up to 1 degree. Now, here's the magic thing. Somebody decided that a nautical mile, which is about a mile, it's 6,076.1 feet. It's not 5,280 feet, which is a real.
Hey, Paul, can I make one correction on that?
Sure.
That is only true for latitude.
It's only true.
And actually, a nautical mile is defined as 1 angular minute of latitude.
It's also true for longitude at the equator.
Yeah.
True. I'll give you that. But then you can I put something in the notes. You can kind of like guess on it by saying it's cosine of the latitude. But that only is an approximation.
Okay, at the equator, 1 nautical mile is 1 minute on the Earth's surface. It's actually a distance that could be measured at different angles at different latitudes as well. But I think I stand corrected that the term nautical mile means 1 minute at some latitude, which would be, but
No, it's actually defined as 1 minute of latitude, period.
1 minute of latitude. Okay, all right.
Longitude is as Ted pointed out, is true at the equator.
I am happy that people are finding these things, because I was hoping not to lie too much. Okay, anyway. Another interesting number is that 4 seconds of time represents one of these, a point moving 1 nautical mile at the equator, or 6,076.1. That is, and I'm going to talk about a ground point, but the ground point is going to just move around the Earth. In 4 seconds, it's moved one of these minutes, 1 minute, which may be a little less and less as you get towards the North Pole. The point I'm trying to make here is that 4 seconds is not a lot of time, and 4 seconds represents virtually not 1 mile or more, or 6,000 feet of motion. So if you don't have your clock, for every second you're off, you're going to be off something like 6,000 feet. So time is important, and that's the point I'm trying to make. Okay, what are some of the things you could, what are some of those options? I sort of mentioned them. You could get a nautical sextant. You can pay that for about $60, and that's accurate to about 1 minute. Or you can spend one for $2,000, and that's maybe accurate to 6 seconds, or a tenth of a minute. You don't need that, but if you're a fanatic about it, you could get a good one. There are also aviation sextants. Aviation sextants don't have a horizon thing. They have a little bubble in them. This is one. And it has a little scale at the bottom here, which you probably can't see. It measures the angle digitally. And you look at it this way, and you turn the knob, and it does the same thing, only it has a bubble level, just like you would if you were measuring a level wall. So that's another one. There's also another trick you can do with a nautical sextant called an artificial horizon. You put a pan of water and you look at the reflection in the water, and what you measure is twice the angle that your sextant reads. So you can divide that angle by 2. So this is another technique. If I'm in the middle of Aquidneck Island and I see the horizon, I can do this with water, oil, and people actually use molasses, but I don't recommend. I recommend being really careful with molasses because, you might be able to eat it after you're done. Anyway, you could just build your own with a protractor. That's probably only accurate to about 1 degree, but that would be really inexpensive. You can buy a protractor at Job Lot. I checked today for $1. And you can also get some fancy stuff like survey equipment, which you can spend $20,000 for, and they're really good. They're good down to 1 second. Dave, do you know the price of a 1 second instrument? My surveyor cousin's on. Dave?
Well, the one that I have, you hear me?
Yeah.
Yeah, the one that I have was about 11 grand. That 1 second one that I have, it's a robotic survey instrument.
Okay.
But you can spend a lot of money on a survey instrument.
Yeah. Okay. Thank you. So that's a choice. Or you could buy one of these go-to telescopes for all kinds of and they actually have calibrated angles on them. Or you can go back to the astrolabe, which goes back to 225 BC and was used. Is still used in 1459, recorded as some of the earliest uses of an astrolabe for navigation. Okay, this is a key point. What is a ground point? If you get anything out of this, I hope you get this. Here's the Earth. Here's a thing here's a celestial body, star, sun, whatever. If I was standing right here and I were to look straight up, that would be the ground. And I see that star or the sun directly above my head. That's the ground point. It's the point where the thing is vertically above the ground. You have to think about that one, but that's the ground point that we're going to try to calculate with mathematics and tables. But the ground point is the key element here of a celestial body. We know where it is from where it projects onto the surface of the Earth at directly 90 degrees above your head. However, if I move away from the ground point, someplace like on this circle, every place I'm on this circle, I will measure the same angle to that ground point. Think about that. If I move around this circle, if I'm at this point and I'm looking at say I'm here and I'm looking in this direction and I measure the angle up, I'm going to measure the same angle everywhere on this circle. And as
Hey, Paul, it may be a little less dramatic, but just imagine you have a ceiling spotlight over your dining room table, and what the people sitting around their table are looking is the angle from the
table
ground point to where they're sitting when they look up at that light in the ceiling.
That's right. So it's not that if you're someplace on a circle, you've got to look back to see this thing. You've got to look back towards in the direction of the ground point. And so if you're sitting around a table, you're all looking up at different directions to see the light in the ceiling. But if you're on a circle, the same distance away, effectively what a circle is, it's Pi Day, I guess we should say that, then you will all measure the same angle with your sextant. I was going to spend some time talking about how that's analogous to standing wave ratio, since it's an amateur radio thing. But if you think of this center point, you're at standing wave ratio. Whoops, sorry. sorry, you're at standing wave ratio 1. And if you're at some other standing wave ratio, you're on a circle around this Smith chart. But I'm going to leave that one for another time. Okay, so to find a ground point, you need to find the Greenwich hour angle of where you are and the declination of the ground point. The declination is basically the height or the altitude. So I'll give you some examples of that. In order to find that, you really have to take advantage of the thousands of scientists who worry about this problem all the time and have been calculating this this position of the sun and the stars for millennia. And so there's a lot of information available and very accurately done, but you can get it in the Nautical Almanac. It's a nice book, and you can buy it for $67 from the government, $10 from Amazon, $5 on your Kindle, or you can look it up online, and all the links are at the end of the presentation. Almost everything actually that I'm talking about is online and free effectively to use. If you were, okay. I have a spreadsheet that I did besides that I'll also provide if you want to play around, where you stick in the data and you get this ground point information. All right, the other thing you need to know, the other thing that we're trying to find out is not just where the ground point is, but where am I? Where am I in all of this? I want to find my position. In order to do that, there are sort of 4 steps. You have to guess where you are. This is not as crazy as you might think. Typically, you got some idea where you are, or at least where you started from, and then you can move in what direction you moved and how far and how fast. And just you don't have to be accurate here, but you have to assume something close to where you are. And I mean close, I could mean 100 miles, 1,000 miles even. It will still work. From that assumed position, not where I really am, but where I just assumed I am, I can by mathematics compute the direction to that ground point, and I can calculate the altitude that I should measure. This is, I will call this tedious, but frankly, with a spreadsheet, it's just a matter of entering some numbers and getting an answer. I also want to point out that if you measure, in order to measure this altitude, you have to be at the assumed position. If you're someplace else, you will measure some other altitude with your sextant. And then that means that you're not at the assumed point. And if you're not there, the question is, where are you? And the technique is to simply move your position by the difference between what you measured and what you calculated. And so if I'm measuring this thing, and I'll show you a graphic of that in a second. If I'm measuring this thing and I get a difference between what I calculated and what I measured, I move 1 nautical mile from that position in the direction of the ground point. So you need the direction of the ground point, and you need a calculated altitude so you can measure that, so you can find a difference. If you're smaller than the measured angle, it means you're further away. And if you're a larger angle, it means you're closer to the ground point. I'll show you this in illustration. Just bear with me 1 second. And now you don't know where you are. You only know that you're on a circle. And what circle you're on. You need 2 ground points in order to find out where you really are. And that's the other key point. So here's some pictures. All right. Here's a star whose ground point is over here in the world, and another star whose ground point is over here. And I can assume a point, and if I was here, I could calculate what angle I would see here and what angle I would see here. And so I would be on 2 different circles. And where I am is where those circles intersect. Now, interestingly enough, there are 2 points of intersection here and here. So if you don't know that you're in the North Atlantic, which is a little tricky to not know, but if you think you're in Antarctica someplace, and you're really up here, then you could make a mistake. But generally, you get some idea that you're in the Atlantic Ocean and not the Southern Atlantic Ocean or the Arctic Ocean. So this assumption is not too bad. The better the assumption, the better the answer, probably. More or less, the better the assumption, the better the thing, the better the estimate is. So here's what it looks like from the ground. Here's where I assume I am, over here in the middle of the Atlantic. And I measure this angle to the, I measure this angle. My angle is actually larger, right? The closer I get here, the bigger this gets. So if the angle is bigger than what I calculated, I take where I was and I move so many nautical miles in this direction to find out what circle I'm really on. And if I measure an angle that's smaller, that is, if I move further and further away, this angle gets smaller and smaller and smaller, then I move away from the assumed position in the direction of the ground point, which is this direction here, or here, depending on which one I'm doing. So this is the key element. You calculate this red line, you figure out, you go with your sextant, you measure this, and you may measure something smaller or larger, and then you get the difference between those two, between this HC, the computed altitude, and the observed altitude, which you did with your sextant. And the difference in angle in minutes is the number of nautical miles that you are away from that position. So you could, we could do a lot of graphs and stuff on that. I'm going to move to this couple more slides. Here's what's happening. Here's our ground point on the Earth. Here's the North Pole, which is, we'll use that as a point. And this is where we are standing. We think we're over here. We look up at the star, and what we're really measuring is the angle along this curve here, the altitude above here, because we're looking at the horizon in this direction. And what happens is we now have that measurement, and in order to calculate where that in order to get the direction that we're actually supposed to be looking, we need to solve this triangle problem, which I'm not going to spend time doing, but I will show you how, and I'll give you a spreadsheet to do it, and I'll give you all the links to figure it out. But basically, remember what we're doing. We have to get a ground point so we know where this point is. We have to guess where we are somewhere over here. And then we have to look towards this star and take an angle measurement from level. And in a nautical sextant, we're going to measure that to the horizon. And that's going to be wrong, but we're going to correct for it. Don't worry about the rest of the details. A position circle is, again, wherever we are on this circle, we're going to measure the same altitude to this celestial body. So we only know that from this, we only know we're on the circle. So we're going to need another celestial body out here to get another circle and find out where they intersect. I've pretty much done this already. The azimuth direction is a little tricky to calculate, but around noontime, when the sun is at peak height, when the sun meets its peak, the sun is directly true south of you. So here's a simple case where at noontime, or not noon, but when the sun is at its peak, the actual Z is 180 degrees. It's south, to south. So that's an example of a direction. All right. Okay. The other thing has to do with how we do this with stars. And with the sun, everybody worries about the sun a lot, but the astronomers needed to come up with a system to deal with the fact that the Earth is actually tilted 23.4 degrees. So if you look at that tilt, you see that there's like an equator, if you will, that's somewhere other than directly on the path to the sun. And that's called the celestial equator. So that's another term that shows up everywhere. And if the Earth wasn't tipped 23.4 degrees, then the two would be the same, but life isn't that simple. However, note that the equators meet at some point. This guy's tipped and this guy's, whichever one you want to consider tipped, but there's a point where the celestial equator and the level to the sun actually cross each other. And that only happens, the sun is only pointing at that point twice a year, at the vernal equinox and the autumnal equinox. This one is coming up on March 20, so it's only about 6 days away when the sun, which is currently south of the equator, will move right into this position where the two cross. And if you could go stand there and look straight up at the sun right here, you would find the first point of Aries. This is the magic reference where has nothing to do with Aries. It has nothing to do with first point. It's just called the first point of Aries. Long story, we'll stop not talking about that. But that's the point of reference for all the stars. So if you want to know where a star is, you have to find this, you have to start with this reference, and then you have to move it forward in time, every day, every hour, every minute, and it goes around, and that's called the first point of Aries, and you have to calculate that. Okay, that point doesn't move 15 degrees per hour like we talked about. It actually moves on the average 15 degrees plus 2.5 seconds per hour. And that's approximately 23 hours, 56 minutes, 4.0905 seconds, approximately, because the solar system moves around and it changes a little bit. And so that's pretty accurate in my mind, but it's not, it's not 100% precise in physical terms. That is what moves. That is the reference for all the stars. And that's one of the things you have to calculate. I'm going to be closing off here in a couple minutes. Dead reckoning is another point, this assumed position thing that I talk about. Assumed position is where you think you are. If I leave Boston on Tuesday afternoon at 3 o'clock and I move directly east, and I know I'm moving 10 miles an hour, I know where I am more or less the next day, because I know what direction I took. I looked at my compass, I moved around, I went out in the middle of the Atlantic, I moved it about 10 knots, and I moved there for 12 hours, and I know approximately where I am. That's what you use for this assumed position. So you try to figure out where you are by just moving, but by just calculating what you did during the last time you took a fix. And that's called dead reckoning. And that's what you use to calculate. An interesting point that I sort of discovered on my own, if I plug in my real position, I take my GPS and I get my real position and I plug it into the formulas at the assumed position, what I find out is where the star really is, or the sun really is. So assumed is only used or the term assumed is used when you're in a boat in navigation, because you have to figure out approximately where you are. If you know where you are, you can use that to figure out where the sun, the stars, or anything is. So, all right. So once you've done this calculation, you basically get a location that will improve the guess that you made. You're always guessing to some degree. There's always an error. And then when you're all done, you just repeat this over and over again every day, or once at noon or whatever, and there you go. And okay, so this time that we're going around, we'd like to think of it as nice uniform 1 second at a time, but the sun doesn't quite do that. If you've seen a globe, you've seen this thing sitting in the side of the globe called an analemma. If you plot it on a graph, you get this, and you can see that, let's see, we're in March here. Notice that this thing can get as much as 16 minutes away from the average time. So this is not a little thing. This sun position changes quite a bit during the year. Okay, I got to keep moving. All right, so where am I? I'm at 71 degrees, 44 minutes, 47 seconds. I checked my GPS. That's where I am. That's where I am west of Greenwich, England. not Greenwich, Rhode Island. And there are nice little tables in all the almanacs that say 71 degrees is 4 minutes and 44 seconds of arc. And so I'm actually 4 hours, 44 minutes, and I did the rest of it, 35.465 seconds from Greenwich Mean Time, which is about 5 hours, right? 4 hours, 44 minutes. If I was in New York, that number would be 5 hours because I'm at 75 degrees. But because I'm at 4 hours, 44 minutes, 35 seconds, that's really my Greenwich hour angle relative to Greenwich, England. Has nothing to do with latitude, but I looked it up. I happen to be at 41:30:04. That's where I am up and down. Okay, I am going to have to stop here because I've run out of time. But basically what I was going to tell you was where to find the sun and how to use the angles. And here's an example of an almanac page, which you can get for free online. Today is the 14th at 1 p.m. Eastern Standard Time, which is not daylight time. I looked it up at hour 18, which is Greenwich Mean Time, not 1 p.m. Eastern Time. At 18 hours, the sun is at 87 degrees, 43.2 minutes. Its declination is south, 2 degrees, 19 minutes, or 20 minutes. 2 degrees means it's just below the equator. So on the 20th, it's going to cross the equator. So here's how you use the almanac to find out where the sun is. And then I did it again at midnight tonight. And when you go to midnight, notice that I changed the Greenwich hour day. I'm not on the same day. So I have to change the day in my almanac because I just moved, even though I've only gone from 1 p.m. Myself, Greenwich Mean Time has moved into the next day. All right, let's see. And the other thing quickly is that when you actually make a measurement, you don't make it on the hour, you make it at some specific time, like 11 hours, 40 minutes and 30 seconds. What do? Well, you look in the table, you can look at the difference between the 2 hours, and you can do a thing called interpolation. And there's an example of it, which I will give you. And I'm going to stop there because we're not going to have time to work on all the stars, but the process is exactly the same. You get the star location relative to the ground point of Aries, and you go through this calculation and you find out where the star is. And I've got examples in the spreadsheet, which you can do, and a lot of links here, including one that I found on how to do astronomy for the visually impaired. Interesting thing. Get your almanac free at these 2 links. Thank you very much for listening. I'm going to end it here, and then we're going to take a break. And I'm sorry I didn't get too many questions, but we can talk about that in the next section if you want.
Thank you so much, Paul. Look at that.
All right.
Let's